Hello everyone, and thank you for attending today's webinar, EBSD Analysis of Deformed Microstructures. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these at the end of the webcast, but if a fuller answer is needed or run out of time, you will receive an answer via email. A copy of today's slide deck is available in the Resource List widget that looks like a green folder. You can expand your slide area by clicking on the Maximize icon in the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click the Help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately one day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce Dr. Stuart Wright, who is our presenter for today's webinar. Stuart was first introduced to EBSD as an undergraduate student at Brigham Young University, working with the first system in North America. He then moved to Yale University to pursue a PhD under Professor Brent Adams. His thesis research focused on automating the EBSD technique. This effort led to the first fully automated EBSD scans in the fall of 1991. After graduating, Stuart joined Los Alamos National Lab and continued work in microtexture and texture analysis using both the OIM technique and conventional X-ray diffraction. Shortly after, TSL was founded. Stuart left Los Alamos and joined the startup company, commercializing the OIM technique, working primarily on software development. He has continued in this role through the purchase of TSL by EDAX. The original OIM system at Yale could index approximately one pattern in 3 seconds. Modern systems have come a long way since those early days, with speeds now exceeding 4,500 index patterns per second. Stuart is closely involved in the continued development of the technique, as well as in working with scientists all over the world in applying the technique to their materials research. Now over to Stuart.
Hi, everyone. Thanks for attending our webinar today. We're going to talk about analysis of deformed microstructures, focusing on plastic strain. But as part of that, if you look at do a Google Scholar search or some of the other scientific literature search engines, you'll find that most of the EBSD papers, or at least a large majority, are focused on deformation. And in fact, I just returned from the TMS meeting in San Diego this week, and even in those areas that aren't necessarily, you might not think of deformation, often if there's any EBSD works, there's still some of the tools that we are being used that we use to examine deformation and plastic strain. In today's presentation, I'll give a review on some of the tools we have in the OIM Analysis software for analyzing strain materials. And specifically, I'll be looking at using the GROD map or GROD maps. I'll explain what those are. And then we'll take a brief look at GNDs, geometrically necessary dislocation density, and step size effects, noise effects, and then also look at Taylor and Schmidt factors, because they also can play a role in interpreting the results. And then also wanted to talk about some of the complementary techniques that are becoming more and more common and provide us a broader picture of strain. Some of this, or quite a bit of the background information of this, is in a paper that we wrote in 2011 in Microscopy and Microanalysis, and that's a good source of information in terms of the tools that we have for analyzing strain materials. And also gave a webinar a few years ago on similar kind of information, more focused on the tools besides GROD, which was new at the time. So without further ado, we'll go ahead and follow that outline. So I often get asked if we can measure strain using EBSD, but strain is a little bit of an ambiguous term. It can mean a lot of different things. I'm going to break it down into two parts: elastic strain. It's important to remember that elastic strain is a second-rank tensor, not simply a scalar value. And plastic strain, which also is a tensor, but also we consider other values of interest, which are scalar values, things like stored energy and dislocation density. And so I'll talk about some of these differences and why this is all important. So when we think of plastic strain, we think of dislocations in the crystal lattice, and they can affect patterns in two different ways. If you have a set of aligned dislocations that, say, a subgrain boundary, then those will create a local misorientation within the microstructure, whereas you may have local perturbations which also create local misorientations, but somewhat in a shorter, smaller order, and sometimes they can cancel each other out, as I've tried to show here. So think of these local perturbations. You can actually have a significant amount of dislocation density, but you could have a net Burgers vector of 0. And we refer to these as statistically stored dislocations, or SSDs, and they will lead to degraded pattern quality, so lower IQ values. The view on the right showing the dislocations is definitely exaggerated. We don't have that kind of resolution with EBSD, but just trying to get the point across that we have a disturbed crystal lattice, and that does affect essentially the Bragg angle for those crystal planes. Now, if you do have a set of dislocations that form maybe an ordered structure that creates some changes in crystallographic orientation within the lattice in a large enough area, then you can get different patterns from different areas. That's what I'm trying to show in this little schematic. So if the diffraction volume were to include that dislocation line there of 4 degrees, then you would basically have a merging of all the patterns together, which would lead to a lower quality diffraction patterns. I tried to show there's a pattern for the blue, the red, and the green, and if the diffraction volume contains all of that, then you would see a merged pattern or superposed pattern. Now, if your diffraction volume interaction volume is small enough, then you would be able to pick up each one of those individual orientations. And we actually see both effects in our EBSD results. So what can we do with individual patterns and in terms of a quantitative analysis? Now, this work is done by Angus Wilkinson at Oxford University, and has been a pioneer in this area, and there's been others who have followed up on this, some of his students as well as others. So in his work, you compare two patterns. So in this case, I've just manually rotated a pattern 2 degrees, and just to show the idea. But you could also not just have a simple rotation, you could have a change in the zone axis positions due to elastic strain. And in that case, the lattice is being stretched as opposed to the dislocations where we have a plastic strain I showed before. So Wilkinson's method, and I put one of his references there, but he's got quite a few really good papers on this subject. The idea is that you create several regions of interest on the pattern. I just show it schematically. They usually overlap. And you calculate cross correlations within each one of these regions of interest. So I've tried to show there. And from those, you'll see a shift. And this is generally at the sub-pixel range. These are very small shifts. And for that, you essentially get a vector. So you end up with a displacement gradient tensor using all the vectors in the pattern. And from that, you can split it up into different parts, the elastic parts and the plastic parts that I've tried to show here. The elastic parts are these, or the anti-symmetric part of the rotations, that is the plastic parts, and they're associated with geometrically necessary dislocations. The symmetric parts are the elastic strain tensor. And so this is you'll note this is a relative measure because we have to compare patterns, but progress is being made to try to go towards an absolute measure. This is still very, it's been around for about, you'll see from the references, more than a decade now, and it's becoming more well accepted in the EBSD community. There is an iterative method that the attempt is to eliminate a need for a reference pattern. So the idea is that you take a pattern, you index it, and from that you simulate a pattern, and then you try to do that iteratively and fit the displacement gradient tensor. But it's very sensitive to calibration and simulation. This is very much, continues to be a research area. But it's improving because of the also emergence of more dynamic simulated patterns, so that you can see through a dynamic simulation, you're able to create pattern simulations that are much better than we had previously, and they look very much more like experimental EBSD patterns. But I won't belabor this. There's lots of research and areas that you can search the literature for work in this area. Just to show that the effectiveness of the technique, if you measure the strains, then you can map them out from many patterns. And here's a hardness index silicon, and you can see the strain fields that develop and the different components of the strain tensor, as well as the rotations. And this gives a very nice result. And the result here I'm showing is from the BLG website. Here's an example of comparing HREBS. This technique is called HREBSD, and here it is versus the conventional KAM, which will be the focus of my presentation. I just wanted to give you an idea of what's going on with HREBSD because I'm seeing it more and more at presentations at the conferences, and is a good development for EBSD. There is a commercial system, Crosscourt. You can see a reference there if you want to look, or an open source system on GitHub. So let me come back to more what we would do with conventional indexing and what we can learn about plastic strain. So as I pointed out, strain kind of manifests itself two ways in the EBSD, in the patterns. One is that you have a degradation of pattern quality, and seen on the top row there for the blue point, or just slight changes in orientation, even though the pattern quality can remain relatively good, especially for small levels of plastic strain. Then you get just slight changes in orientation. And you can see that in those two patterns, if you look very closely, are actually just slightly different from each other, indicating a change in orientation. So this shows up in the maps in a couple of different ways. So if we focus on pattern quality, then you'll notice in this map it's a partially recrystallized material. You'll notice the dark regions are the strained areas, and the light regions are the recrystallized grains. And that is quite apparent in this map, but it's also apparent if we look at changes in orientation. So in this case, it's a standard IPF map, inverse pole figure map, showing the orientation as a color. And you can see in those strained areas that the orientation can change quite a bit from one end of the grain to the other end of the strained grain. And whereas the recrystallized grains, the color is solid. So those subtle changes in color tell us that there's strain there. And we can be quantitative about this. So as I mentioned, plastic strain is very evident in the IQ maps, but there's a lot of other things that create contrast in the IQ maps. One is clearly sample prep, and that is actually an indication of strain. The other thing is that if you have second phases, they often show up in IQ maps as lower or higher intensity due to the nature of the second phases versus the matrix phase. Cracks obviously show up, pores, grain boundaries show up. So that's a problem because grain boundaries would appear to be strained material when it's just a grain boundary effect. And so strain is actually a lower order effect that we would see in the patterns. So even grain size you can see here can have effects, and even orientation. So these can be pretty subtle, and they are all effects that we can see in an IQ map. Now, local misorientations also show up. EBSD is quite good at identifying local misorientations. Conservatively, 0.5 degrees is achievable, but with a little bit of care, you can get down to around 0.1 degree in terms of misorientation, at least with this technique, with standard Huff-based indexing. Mapping methods, so there's a lot of different methods of trying to characterize these misorientations, because you'll see the grouping of misorientations. In this case, the red boundary segments indicate low angle misorientations, and you can see those in those deformed grains. So we have different ways of analyzing that. We have what we call kernel or window-based techniques, the most popular being CAM, kernel average misorientation, which I'll explain what that is. But there are others that I refer you to the references I gave at the beginning on the outline to get more information on some of the alternative approaches. The other grain-based ones, GOS, GAM, and I'll talk a bit about GOS, introduce that, but once again, for the others, go ahead and go to the paper that I referenced earlier. There's another one called what I call reference orientation based, or GROD, grain reference orientation deviation. I'll explain what that is. And there's a lot of different forms of that. So let's look at the CAM, kernel average misorientation. The idea here is you have a kernel of points. For this case, I'm showing them points collected on a hexagonal grid in a scan. And what we do is we calculate the angular deviation from a point at the center of the kernel. And usually we look at the ones on the perimeter, as I've shown there. But usually we're looking at nearest neighbors. So you can go out as many neighbors as you want. Obviously, the nearest neighbors is the closest you can do. And you calculate all these orientation deviations, and then you calculate the average, and you color the point according to that average. So in the map at the right there, the blue points have a very low kernel average misorientation, and as you move towards red, those are points that have a high kernel average misorientation. So the points in red are areas that have a lot of change, a local misorientation, which is an indicator of plastic strain in the material. And you repeat that, I've failed to mention, you repeat that for each point in the data set. Now, another one is we call the grain orientation spread. This is a grain-based idea. So you have to first partition your points into grains using our standard grain reconstruction approaches based on nearest neighbor misorientation. So the first step in this is you calculate the average orientation for a grain, and then what you do is for each point in that grain, you calculate the deviation in orientation from the average, and then you calculate the average of all those, and that gives you this grain orientation spread, or GOS. And so each point in the grain in this case gets the same color, and because you're just looking at the average. And once again, we repeat that for each grain in the data set, and then we end up with a map where each grain is colored according to this average deviation. So you can see which grains have a lot of misorientation in them, and local changes in orientation, versus those grains that may be very clean, and recrystallized grains, for example. Now, there's another grain-based one, but now instead of each point getting the same color, we're going to allow some deviation. So one approach to this is you calculate, once again, an average orientation for the grain, and then you calculate the deviation at each point from the average. But instead of assigning each point that average value, you actually color each point according to that deviation. And so what you see in that little example schematic there, you'll see that the blue grain is one where it's very close to the average orientation of the grain, whereas the red one is quite far away, 5 degrees. And those can actually be quite large at times in a very strained material. And once again, repeat for each grain in the data set. So this is the kind of map you might see. And what does it show? So originally I thought of these showing the change in orientation relative to the grain orientation prior to deformation. But I'm going to explain why that isn't quite true. And much of this is covered in JOM paper we wrote a few years back. So here's an experiment that we've done using a in situ tensile stage, where you can see that sample can be tilted in that stage, and a little dog bone there, and then we can monitor using EBSD the changes in orientation as the material is strained. So just to show you, here's the force displacement curve. We're scanning a relatively small area because we want to see what's going on within the grains, and we want to do it fast enough that we capture it. So we repeatedly scan that area that you see there after 1% change in displacement, in elongation. We actually, our initial point, our 0 point is actually after just loading it up. So it isn't exactly 0% strain, just so you're aware of that. So here's the inverse pole figure maps, the standard kind of color maps you see, and you'll see two effects. You do see some change in the image quality, and that is somewhat due to repeatedly scanning the same area. I'm not sure quite why we see the dark points coming up more and more, but that is what we see. But you'll also see something, I think, more critical as you start to see some subtle changes in color, and this is what we're going to focus on with our tools, because these are the change in color is a change in orientation. So I mentioned the kernel average misorientation maps. Here they are for this, going from 0% to 10% strain. So the first one is, the top row is our nearest neighbors, the first orders, and you can see some change there, but it's not a whole lot of development. The step size is too fine to really pick up any big changes. We're near the order of the precision at that point, and I'll come back to that point later in the presentation. Now, the second row, our fifth order, which is a relatively large, so fifth nearest neighbors, which corresponds to a half of a micron step. And then you can see some development in the strain kind of flow fields within the material, within the microstructure. One point that comes out immediately is that it is sensitive to step size, and I'll come back to that in more detail. So here's the GROD maps, the grain reference orientation deviation maps, where we're comparing the orientation at each point relative to the average orientation for the grain. And you'll see that develop quite nicely. You can see, so areas in blue will be very near the average orientation of the grain, and areas in red are quite far away from the average orientation of the grain. In this case, almost 9 degrees. And so you can see kind of a band in the center of that large grain at the center of the scan area we're looking at here is quite close to the average orientation. And then as you move to the left and the right of that, you can see rotations away from that average orientation, kind of suggesting that the grain is bending away from that central orientation. Just the usual notes, all the usual caveats apply with a free surface. That's what we can do in situ. We can't look in the bulk with EBSD, so we certainly know that it isn't necessarily completely representative of the bulk, but we hope it gives us some indication of what's happening. We're going to focus on the data set at 10% strain because that's the critical one, and compare it to the one at 0% strain. There's lots of ways you can select that reference orientation. So in this case, we focused on the average orientation for the grain. That isn't necessarily the only one you can use. So there's two that we have suggested. One is the average, and that goes back to some old ideas that we originally got started with EBSD, even before the paper I show there, even though that's one of the earliest. But there is another one. We could use the orientation of the point in the grain with the smallest cam. The smallest cam would indicate a point maybe that hasn't gone through much plastic strain and may be closest to the original orientation. And that is something you can certainly do. And it comes with various challenges, but it's one that we found works as well. Some others have been suggested by other authors, using the point in the grain with the maximum confidence index, the one with the maximum image quality, the one with the best fit. And all these go back to the idea that these would be related to the point in the grain that most likely is closest to the original orientation of the grain. Some others go to minimize the overall deviation or maximize the overall deviation. And then we've also thought, why not use the one closest to the geometric center of the grain? Just not so much that it matches the original orientation of the grain, but in the sense that it gives us an idea of what's happening at the edges of the grain versus the interior. So here's different maps, and you can see them all here. You can see some are similar, some are quite different, and where they show the maximum orientation happening. And that's not a surprise. You can see that the largest misorientation in this case would be 12 degrees, obviously for the one where we're trying to create the most misorientation for the GROD max dev, as I shown there. So I mentioned that we may be trying to find the pre-deformation orientation with these maps, and all these are like, as I explained before, are created to try to get that idea. So, but what are we really trying to measure? We're trying to capture the change in orientation with respect to the grain orientation prior to deformation. Then our in situ data can help us determine which is the best measure for capturing that. So for each grain in the scan, we can compare to the reference orientation of the corresponding grain in the 0% strain scan, which I've tried to show here. And you can see I'm calling that GROD 0, and you can see the result here. You can see there's a lot less strain in the material than we get if we use some of the other measures we talked about. Just as a note, it's not necessarily easy to do this point-by-point comparison between the scans that say 10% and 0%, because the sample is moving as you deform it, especially in a tensile. We may not be right at the center of our area, and so you can see that in this case we have a slight shift. I've corrected for that shift, and then also done a few tricks, because obviously the grains are changing shape also as we deform, and so I've kind of had to do a little trick to try to fill in. It's a little easy in this case, because if I assume the GROD 0 is the same orientation within the grain, which it pretty much is, at 0% strain, then I can use that. Now, if my starting material had more strain in it, I couldn't make that assumption. So here's our GROD 0. So comparing the 10% versus 0% strain map down at the bottom right. And if you look at that, you can see which one maybe matches it best. I would say the MinDev, the average, works pretty well. Actually, the centroid works pretty well. But some of the others are quite different. And so you can interpret that and try to understand that. But what does it really mean that none of them match perfectly? Well, I think what we're learning is that the GROD 0 map tends to show us the more general change in orientation. That is the independent rotation, the rigid body rotation of the material as a whole. The other maps tend to emphasize the fragmentation that occurs during deformation as the material tries to maintain structural compatibility with neighboring grains, all of which are also rotating. So more like the Sachs model. Those of you not familiar with this, the Sachs model is a uniform stress model, an isostress. So each grain, it's assumed that each grain of the material has the same amount of stress during deformation. And what that results in is that you have variable strain within the material. And so you start to lose incompatibility, is the weakness of that. Now, the Taylor approach assumes isostrain so that each grain has the same amount of strain in the material, but variable stress. And that leads to you have a compatibility, you get rid of the compatibility issue. And you can see some of these effects, and this is well understood with slip lines and other types of analysis, which I will actually come back to later. And so if we go back to the previous slide, you can see that the idea that the Taylor model would be uniform strain within the material, whereas in order to make the Sachs model work in a sense, you would have to have different amounts of strain in the material. So our GROD maps give us some insight into how strain is happening. As I mentioned, the GROD 0 shows the overall deviation, and whereas the others show the fragmentation. The other GROD maps provide that fragmentation picture. It's not a valid assumption that the points of the orientations near the reference orientation represent material that's stationary, but it does give us an interesting picture. And also, it's always important to remember when looking at these types of maps about plastic strain that they provide a description of the current state of the material, but may not always provide us a historical evolutionary context of the material as it moved towards that state. Some interesting things. We also in this material, we looked at the misorientation at the grain boundaries. You can see for that red grain boundary, it really changed orientation quite a bit as the two grains are moving away from each other. Other boundaries, the grains seem to have moved in a more compatible way. And you can see, for example, the blue one hasn't changed a whole lot in orientation. But it's also important to recognize that that the changes in misorientation seem to be greater than we assumed from the G-rod map. You know, you're seeing misorientations here, a fairly large amount, more than what we were seeing within the grain itself. But we have to remember that the angle is only one part of the misorientation. We also have to consider the axis of rotation. And if you do that, you get these kind of maps. So here we're showing the rotation axis, the top row in crystal space. So for example, the points colored in blue are points where the rotation is about the 1-1 axis. Points in red are rotations about the 0-1 axis. And you can also plot these then in sample space. There's a couple of different ways you can do this. I'm just showing one example here. So grains that are very sharp in color, the rotation axis is pretty much lies within the plane. As you move towards white, and perfectly white, the rotation axis would be normal to the plane of measurement. And so you can see that development there as well. And there's a lot of interesting things going on. I won't go into any detail of that analysis. We've tried to start to look at that, but it provides an interesting picture. If you zoom in on this a little bit, there's something that I would call a misorientation degeneracy, or at least for the axis. As the misorientation gets small, the axis is not well defined, and we're also reaching the precision limits of our measurement technique. And you can see that in these maps. You'll see that the points are not well defined here in this circle. So the G-rod angle map is blue, indicating very little misorientation. You can see the points are speckled there. The colors aren't consistent. But in other areas where the misorientation is large, like in the yellow-orange area there, that you can see the axis is well defined. And it also seems to give us some indication of maybe some subgrain development as well. And so we're kind of excited about this technique and seeing more and more people using it to examine the evolution of straining the material. So can we do something even more quantitative? Can we look at geometrically necessary dislocations? So geometrically necessary dislocations are those essentially that give us the rotation that we see from pattern to pattern within an individual grain. So how do we get from orientation A to orientation B? And it's basically a geometrically necessary dislocation. And so they can be connected to the orientation, especially the orientation gradient, measured at a point by EBSD. So if we express the change in orientation with our vector G, I give you a few equations here. My advisor taught me I should always show an equation or two in the presentation, or it's not a real presentation. Sorry. But we can connect the Nye dislocation tensor to the orientation gradient through that permutation tensor there. The Nye dislocation tensor is alpha. And that can then in turn be connected to the density of dislocation by the summation equation there, where rho is the scalar dislocation density, and the couplet B and Z tell us about the dislocation type, where B is the Burgers vector and Z is the line direction. So what that means is we have if you can imagine collecting data on a square grid, we can interpolate it from a hexagonal grid as well. Then you basically have a misorientation between a point and its neighbors. We can just focus, I mean, typically you would just focus on the one to the right and the one below, but we can actually create a little bit better if we consider the others and do a little bit of a curve fit, if you will. Now, this is a three-dimensional quantity, and so if we were to do some kind of 3D serial sectioning, you could pick that up and add that too, but we will focus just on the in-plane measurement. So from that, you basically end up with a map that looks like that. Obviously, from the previous slide, it's going to be closely related to the CAM. What we do have to enter is the slip system, and so you will end up with different GND density maps depending on what slip system you use, regardless, they will be quite similar to the CAM, basically scaled by the step size. There was a really good talk that I remember Stefan Zeffer gave. Stefan is at the Max Planck Institute, or when he gave this at the Max Planck Institute for steel research in Germany at Dusseldorf. And he points out that both geometrically necessary dislocations and the statistically stored dislocations, SSDs, they're a direct indication of plastic flow, or neither are a direct indication of plastic flow because they're stored, they're immobile. And so they do indicate the heterogeneity of flow, which we certainly see. But he surmises that they are only a small fraction of stored dislocations, around 10%. Other authors have indicated different feelings about that, but it's something you kind of should keep in the back of your head as you do this. But GND density depends upon the measurement conditions, step size, angular precision, and I'll come to those points. But regardless of those maybe things that we don't necessarily always understand, they are always interesting because they do give us the indication of plastic activity at obstacles. For example, we see pileup at grain boundaries. And they are obviously areas of high dislocation, areas of, say, nucleation for recrystallization, or potentially corrosion or other things. So they are important and do give us lots of information, even if quantitatively we may not be exact. Just as an example, here's some 3D results from Stefan's group showing dislocation of different kinds within a block of material. Okay, so what are the step size effects? I'm going to just show a quick example there in the title slide. Here's some experiments on cold rolled brass. We did two different sets of experiments, one at 250 nanometer step sizes and one at 20 nanometer step sizes. And then using coarsening of the data, we can actually pick up some other step sizes. So there's 3 different scans here, 30%, 20%, oh, there's 4, sorry, 30%, 20%, 11%, 4.5% cold work. And then you can see that the measured GND from our measurements, EBSD measurements, goes up as the step size goes down. That you see there. And so it's clearly step size dependent. And you can see that in the CAM results. So you can see on the left are the nearest neighbors, and the ones on the right are the 5th nearest neighbors. And so the ones on the left are pretty noisy. And that's because as I go to the nearest step size, the misorientations are small. I'm starting to reach the limits of the EBSD precision. As I go to larger step sizes, the misorientations tend to be larger. And so I pick those up clearer, and so I tend to get a little bit cleaner results. Regardless, you can see some of the same features develop, which is good, even though the step size and so maybe the magnitude differs. You do see some of the same features regardless of the step size used. So why does this happen? One is a precision issue, which I referred to and I'll come back to, but also is because of the relationship of SSDs. Imagine that you had a row of dislocations. You measure the misorientation at one side, and you measure the misorientation of the other side, and from those you calculate the GNDs. You can see that a coarser grid or larger step size, you would pick up the misorientation well, as indicated by the green line. So if I had a large step size, I would get larger misorientation from the 2 endpoints. But if I had a lot of SSDs essentially canceling each other out, then my overall misorientation would be small for my, the 2 endpoints, and so my coarser grid size wouldn't really help me. And so we believe remember, we're measuring GNDs. We're not measuring dislocations per se individually. We're measuring them more based on the change in orientation. So that's the point to remember here. So what we find is the smaller step sizes produce smaller cams, so we have a smaller step size, and so we are more sensitive to the orientation noise. So this is more of an issue at low levels of strain. And more strain generally, the other challenge we have is more strain generally means noisier patterns. So our precision also drops off as we have more strain. And if this is really a big issue in your material, then you should probably try the HREBST techniques I referred to at the beginning of this presentation. So what about noise effects? I've alluded to this, and it is something we have to consider. Much of what I will talk about is from a paper that we wrote and some of what I wrote about is a paper wrote in 2015, but some others I'll reference as well. So we know that as as we get more strain, our patterns get poorer. And so this results in our less of ability to precisely locate the bands in the patterns using the Huff transform, which leads to more noise in the orientation measurements. So as an example, here's just a single crystal silicon. And if we analyze that, you can see it's a tight cluster for that set of measurements. It's a pretty big scan. That's part of the reason for the imprecision. But you can see it's pretty tight around the center. This is an 001 pull figure for this material. And so you can see it's a tight cluster. Notice the pull figure goes out to only 2 degrees, not the full pull figure that in the bottom left. Now, if we add noise to the patterns, and just simply add a Gaussian noise for this example, if we add a certain amount of noise, then you can see that that cluster isn't nearly as tight. There's more noise in the pattern. So as we increase noise, the precision goes down. So in CAM maps, we often see that the CAM values are higher near grain boundaries. And so we were interested to see, is this real? We would suspect it could be real. Dislocation pileup at grain boundaries certainly could happen. And so, or is it just an artifact of imprecision? So we've looked at this in detail, and this is because there is a grain boundary effect on precision. As if the interaction volume contains a grain boundary, then basically you get a contribution from the lattice on either side of the grain boundary, as I've tried to show in this example, where you have a blue grain with one orientation, a red grain with another, and you can see the superposition of the patterns from those 2 grains in the mixed pattern in the center. And what that results in then is, if you look at the right, I've used the Huff to try to find, in this case, we found 6 bands, 2 from the blue grain and 4 from the red grain. We're still able to index it. Obviously, there's a majority from the red grain, but so it identifies the red grain as the correct solution. Now, if we do that, when we do indexing, we use all the bands we use to calculate the orientation. So we end up with kind of an average orientation, as we know that we're never going to get to position those bands perfectly precise. And so if you look at that for this grain, we have 4 contributing to the average orientation for the red grain and 3 contributing to the average orientation for the blue grain. And we use triplets, so really just 1 contributing to the blue. Now, if we had an orientation from or a pattern from a grain where there's really on the right from the interior of the grain, then all 7 contribute, and we have 35 triplets contributing to that average orientation, giving us a more precise measurement. And you can see that effect in the EBSD measurements. As you get near the grain boundaries, the confidence index goes down, and that's an effect of the orientation precision. So, do we believe the CAM results near the grain boundaries because of this effect? Well, one thing you can do is increase the number of bands that you use, and that certainly improves the precision at grain boundaries, you've noticed. So we took a look at this cold rolled brass that I mentioned before and looked at the CAM results near the grain boundaries, and they do go up. But from our measurements, if we look at a perfectly recrystallized material there, the black line, you can see it does go up in the grain boundaries, we suspect due to the precision effect, but it's very slight. And so we do see some increase due to reduced precision with increased dislocation density at the interiors of the grains. That's way out there at 5, and you can see a slight rise. And we suspect that rise would be just about the same as we get near the grain boundaries. And you can see, though, that it's much larger than that. So on the left, the arrow there is due to increased dislocation density. So yes, there is an effect near grain boundaries, but nonetheless, majority of it is due to dislocation density increase. So we want to look at an example for real materials and the effect on the G&D measurements. So we're going to add noise to the patterns artificially. And then we're going to use some of the cleanup routines we have to see if we can improve the strain measurements. So there's a simple one, Gaussian weighting, where we just average the orientations together of nearby pixels. Another one called the Kuwahara filter, which is a little more complex. We look at the neighboring grains, look at the median or mean and standard deviation, and replace the center with that, which is a well-known image processing technique. And that will clean up the image, but it can create artificially subgrain boundaries. In this case, it seems to fit well. And there's one called a bilateral filter, which is basically a mix of these two ideas. So here's an example for a steel, and you can see the cam on the right without any of this filtering. And here's the effect of the cam if we do this filtering. As I mentioned, the Kuwahara will bias towards subgrain boundary creation, and you can see that in the result there. The Gaussian is simply smoothes things out. The bilateral is a mix between the two. And in fact, if you play with the bilateral, the different parameters, you can get it to either match the Kuwahara or just the Gaussian. Now, there's another technique we've pioneered in recent years called NPAR, where we look at the average of the patterns nearby of the neighboring points, and we calculate an average one. So we essentially clean up the pattern quality, get a higher pattern quality for indexing. So we can use that as a way of filtering and improving the orientation precision as well. So we're going to do an experiment on 75% cold rolled copper. Once again, I'm going to add some noise to this. We're going to focus on the small step size GNDs because those are the ones where noise is going to play the biggest role. So what happens is you add noise. So I've added noise to the patterns artificially. It shifts this curve of the GND densities to the right. You'll see in the dashed line there. And that's because our precision has dropped. And we're getting, basically it increases the number of small low angle boundaries. Now I've applied the different filtering schemes, the Kuwahara, the bilateral, the Gauss, and NPAR technique. And the good thing is they all seem to return back to the original. And I was actually surprised in doing this, how well this worked. So if you do have concerns about precision, I guess my takeaway is that you can use these filters to try and improve things a little bit. We always have orientation noise, and so it may be worthwhile doing that. Now, let's talk a little bit about Taylor and Schmidt factor analysis. These basically are focused on slip systems, and they help us understand our material. Now, the Schmidt factor is a pretty basic idea. You have a stress, which is equal to force over area. That's pretty simple. But if you have it on a slip system, then we're going to resolve it to that slip system, have a resolved shear stress. And if you go through all this math, the point is at the bottom, this is a geometric effect. So we specify the slip system, and then using the Schmidt factor, we can have an idea of how likely that slip system will be active or not. And so here's an example. The blue grain here is less likely to slip. Its slip system is not well oriented, and you can see the values there. Whereas the higher values, the red, are more likely to slip. And so you can see the difference there. Now, we can also use a Taylor factor, which considers the idea that slip is going to happen, more likely to happen on multiple slip systems. Once again, you have a deformation gradient tensor, like I kind of talked about earlier, where we look at a point in the original space versus the deformed space, tracking the same point. From that, we can calculate a displacement gradient tensor and break that into skew symmetric or symmetric and anti-symmetric parts, like I talked about in the introduction. So you have the elastic part and Cauchy strain and the rigid body rotation. And similarly in the crystal, you have that, and so you have a magnitude of slip on a slip system where you know the slip plane normal and the slip direction. So it looks like lots of math, and you come up with, but if you go through that, then you come up, Taylor's analysis requires we find a set of 5 slip systems which satisfy, which will maintain compatibility within the grain with the least amount of plastic work and achieve the strain necessary. And so you can go through various machinations and you end up with a Taylor factor, and it tells us something about how much effort it's going to take to strain the material. So here's slip on 5 slip systems, once again, for 2 different grains. And in this case, all 5 slip systems will be active. They have different amounts of slip on each slip system. Just so you know, in this case, it's the opposite direction. The lower values are more likely to slip. So I've had to change the gradient, color gradient. So the inputs are the crystallographic orientation, which we obtain through EBSD measurements. We also have to input the slip system interest, just some examples there, and the applied stress state. And so here's an example where I've assumed pencil glide in along one directions for stainless steel. This is the example, in situ example we've shown before. And you can see there's some similarities, but it doesn't match up perfectly with what we expect from the GOS, what we would expect from a GOS measurement. And this is because the local stress state is not the same as the bulk stress state. And so it's not perfect, but it does give us some ideas, and we do see some correlations, and it is a way to analyze the materials and to some kind of crystallographic or slip model that help us understand what's happening in our material. Now, there are also some complementary techniques. We've focused on EBSD here, but I think more and more people are using different techniques to try to get at the complete picture, because what we have is only a partial picture with EBSD. For one thing, it's a 2D, and there are other ways of doing that. So let me talk about some of these and how they relate to EBSD, because I think it's important, and we get a lot of a lot of information from these. So let me look at 4. There are others. Transmission electron microscopy, kind of going in order of different resolution here. ECCI, electron channeling contrast imaging. DIC, digital image correlation, or HRDIC is what I'm going to focus on, high resolution digital image correlation. And HEDM, high energy X-ray diffraction microscopy. Sorry, need a drink there. All right, so here's an example, courtesy of Tim Ruggles at Sandia National Lab and Josh Katcher at Georgia Tech. These are bright field TEM images compared to, this case, HREBSD work that they've done. And so what you can see are some dislocation tangles with the blue arrows indicating that. You can also see a twin boundary in red. And you can also see a line of dislocations there that, indicated by the black arrow. So by aligning the G vectors differently, then you see different things in these images. But the key thing I want to show is that there is some correlation to the EBSD. It's not one-to-one in terms of strength or whatever, but you can see these features. So the red arrow is that twin boundary. The dislocation line there in black, you can see, shows up in the HREBSD. The dislocation tangles also show up. So we can look with the TM, obviously, at higher resolution, and that gives us, we're getting a complementary picture of what's happening within our material. Which is good news that we see similar features. Another one that I'm seeing much more in papers and at conferences is the use of electron channeling contrast imaging, ECCI. In this, what you have to do is you can do this in the SEM, which is convenient, as we can also, as EBSD is also an SEM-based technique, is that you have the BSE detector mounted below the pull piece, and you lightly tilt the sample into a 2-beam condition. This is going to be done typically at a much higher or a smaller working distance, and you slightly tilt it, and if you get it in the right position, then you start to see the evidence for dislocation, individual dislocations. And you can see that in the picture at left, and then once again, HREBSD on the right, trying to show G and D densities. And you can see evidence for these. It isn't one-to-one all the time, but we are seeing similarities, especially as you start to count the dislocations and get an idea of the density. Another one that I think is exciting and seeing more and more is high-resolution digital image correlation, HRDIC. Now, if you think in the macro sense, you apply some markers on your material, you strain it, and you watch and see how those markers move. That's a well-known idea to get ideas of strain fields. Now, what's interesting for the high resolution is they've come up with techniques to put some kind of speckle pattern with another material down onto the surface. And then using image processing, you can see how those markers move. And now we're doing this down at the similar kind of resolutions that we see with HREBSD. And so you know how those move. So once again, you have a displacement field, and then you can turn that into some kind of intensity mapping that I'm showing here. So this is courtesy of Sam Daly at UC Santa Barbara. And you can see the development of strain within the material as you go through the strain process. You can see the dog bone there, and you can see 3 measurements on the stress strain curve with A, B, and C, and then the strain field that developed in the microstructure. And if you do the EBSD prior to putting on the speckle pattern, then you can map out the grain boundaries from the original measurement and see how things are changing. And now those grain boundaries may have moved a bit because of the straining process, but what you're seeing is the overlay from the pre-strain applied, before the strain is applied. So how does this correlate to EBSD measurements, such as the CAM and G-Rod and others? So this is courtesy of Professor Gatan de Fonseca at the University of Manchester. And Zhao has shown that in the DIC, what you're noting in this cartoon, that you catch the in-plane slip, the plastic rotation, the rigid body rotation with HRDIC. And then he's noted that if you use the 2 different types of GRODs that we talk about, that you capture some for the GRD0. So going back to in an in situ experiment where you have the pre and post orientation measurements, then you capture 3D plastic rotation and rigid body rotation as a misorientation, but not necessarily a deformation. Whereas with the EBSD, the G-Rod compared to the average orientation, you capture the plastic rotation, but no rigid body rotation. So this is an interesting way. It gives you different ideas of what you're seeing in the microstructure as you deform the grain. And just one more slide on the HRDIC. Here's, this is courtesy of one of Professor Fonseca's students, former students, Alan Hart. And you see this high-resolution digital image correlation, beautiful map over quite a few grains. You can see the strain is horizontal there for tensile. I've tried to illustrate. And let's look at 3 different grains with different amounts and character of the slip lines. So grain 1 is single slip, grain 2 double, grain 3 triple, grain 4 we start to see a significant cross slip, and then the last grain has somewhat of a diffuse nature in its slip. And you can see both the digital image correlated measurements and the EBSD, in this case the G-Rod average measurements. And you can see some interesting features. I know when I look at them, I tend to see that the cross slip areas tend to show higher intensity in the G-Rod average. But I haven't spent a lot of time with this, but it is an interesting result. Something to keep in mind, certainly. Now, going up another level in resolution, there's also the high energy X-ray diffraction microscopy. And this is increasing the resolution as these measurements, as they've improved these measurements over time. This is results from Matt Miller's group, and one of his students, Kelly Nygren, at Cornell. And I think this is a really nice image. So what you see is a grain, or it's tracking the stress that develops within a grain with strain. And you can see where this orientation is in Rodriguez space. So not only do you track the strain, but you can track the change in orientation. And so this could be, the nice thing is this is done in the bulk, so then we can start to compare this to EBSD measurements to check and see we're seeing the same thing in the bulk as at the surface. But you can see in this the colors indicating the amount of strain in the material, and then you can also see the orientation moving within the grain. So you capture both the development of strain with change with orientation. So that is a nice example as well. And once again, I mentioned that I was at the TMS meeting this week in San Diego, and saw lots of good examples both of this technique, but also all the others. Some great talks using HRDIC, using HREBSD, using HEDM, using ECCI. And so all these techniques are at your disposal. Some are hard to use, some are easy to use, but there's certainly good work out there and people to partner with to improve these things and link everything together. So I hope what I've shown is that that elastic strain requires advanced techniques for measurement, the HR-EBSD cross-correlation type results. It also requires good high-resolution patterns, high-quality patterns, and that's an area to explore. With traditional conventional Huff-based EBSD measurements, we're able to look at plastic strain. I've noted the GOS, CAM, and GROD. Those tend to be the most common that I am seeing, but you do see some of the others used as well that I mentioned. You can look up in the papers or the past webinar we gave. It's quantitative. It is step size dependent and sensitive to other calculation parameters. That's something to be aware of. And the sensitivity to the calculation parameters I haven't spent a lot of time on here, but it is part of the paper I mentioned. It's difficult to link EBSD results to absolute values of plastic strain. Yeah, I'll say that right out, but it is very useful as an indicator of local strain concentrations. Where is the strain building up within the microstructure? That kind of picture is EBSD is great for. Do be careful in interpreting the results, both in terms of orientation precision, and this goes to the quantitative part of this, the absolute strain part, as opposed to the flow fields and indicators of local strain buildup. But you also need to be careful and not always assume that what you're seeing in the microstructure is that's captured well, but how the material got there is not always well understood, not always captured. That has to be interpolated and inferred, although the in situ measurements can help understand that. And then I also really want to point out the comparison with dislocation slip models. The simple ones like the Schmidt and the Taylor factor are very useful for understanding your material, and then adding in other complementary characterization techniques can even further answer those questions that may still be out there. And so I think as you read the scientific literature, you can see that these techniques are all giving us a better idea, and we're learning more and more as to how our materials are behaving, and hopefully we can become even better at predicting material behavior and understand the linkage between microstructure and properties. So with that, I will close the webinar. There's lots of other resources we have at EDX. I encourage you to go to the website. You can see the webinars, have fun reading the blogs, and there's other places to look. And of course, there's always the scientific literature out there, and hopefully we link you to some of that as well. So with that, I'll take a look. Couple of questions, if we can. I can't answer them all, but we can certainly reply to you by email. So there's a good question about, which I have not talked about, and that is essentially resolution. What are the smallest grains we can measure with EBSD? And it's going to differ from material to material, and also on the microscope, the capabilities that you have. It's, grains larger than a micron are pretty straightforward. As we get smaller than that, then that starts to become a bigger issue. But we can usually get down to grain sizes, say, conservatively down to 50 nanometers, and then if you need more resolution, go to TKD, transmission Kikuchi diffraction, which we also have some presentations on and webinars, so look at that for going to higher resolution or to smaller grain sizes. I do make the point, while we can image a small grain, say a 50 nanometer grain, the problem is if you're going to do any types of strain work, then you're going to need enough measurements within the grain to get at the strain fields to capture those local misorientation changes. So you may need to go to you may not be able to do 50 nanometer grains, and while you can image them, you may not be able to capture the strain within those. It looks like there's quite a few questions here, so I think we'll have to probably try to take a look at maybe a couple more. You've all asked some very good questions. There's a good question about in situ experiments. And that is that we basically, it's a dynamic process. And so deformation, we have to stop it and measure, scan areas. So the material will relax a little bit. In terms of dealing with this effect, obviously we want to go as fast as possible so that we reduce this effect. So there's kind of a couple of things at issue there. One is we want to go fast, so we want to use maybe a faster camera. The challenge is as we go faster, sometimes we can lose some precision, so you have to find a balance there. But certainly we want to go fast, so you probably want to use a lot of current and so that you can go fast and get a good measurement. But you may also want to think about your step size and the scan area you're going to cover. You noticed in the in situ measurements I showed, we only captured a few grains, focused our analysis on one big grain. And so it might be worth doing multiple samples so that you can do it fast and do small areas. And that way you can get more grain orientations involved by covering multiple samples as opposed to covering one sample or one area on the sample. So that is something to think about. Certainly a good point. Be careful as you mix these different images. Make sure you understand the colors. For example, in an IPF map, blue refers to a certain orientation, but in a CAM, blue, at least by the default grain coloring schemes we use, blue will be basically the lowest deviation, so closest. For example, in a GROD map, it would be closest to the original orientation or to the average orientation, whereas blue in a CAM map is just an area with low misorientation, whereas blue in an IPF map refers to the 111 orientation. So the colors don't just transfer from one to another. You need to think a little bit about and check and make sure you're using a color scheme that works. A great example is the Schmidt and Taylor factors. So in the Schmidt factor, it goes the highest means it will slip, whereas in Taylor factor it's the opposite. So you might want to use opposite color gradients if you're going to compare those two results. So that's something to think about as well. One point, I'm seeing several questions about SSDs. I'm sorry, I must not have explained that well. Local misorientations, so SSDs will not produce local misorientations. So basically, you have rotations that are canceling each other out. And so EBSD will not pick up SSDs. You will see it in the quality of the patterns, but that's a little harder to be quantitative about. And so SSDs are something we miss. What we do pick up are the GNDs. So that is something that you should be aware of. So with that, thanks for your attention. I'll go ahead and address the rest of these by email. Thanks again especially those who've asked questions. Thanks for asking questions, and hopefully we can get you answers that can help you understand for your materials and the challenges that you're facing. So thanks again, and tune in. We'll be having a webinar again, more on an EDS topic next time, but we'll certainly have EBSD ones in the future and hope that you enjoy those as well. Thanks again.